My name is Will Remus. I'm a technology writer for the Washington Post. Probably know less about computer science than almost anyone in this room, but I have been covering and writing about the technology industry for 12 years, including AI off and on. And I want to thank Tom Goldstein for inviting me to moderate today. Tom's been a great source on a couple stories I've written recently about AI. I want to start by, well, first of all, the theme that we're gonna address here is what makes machines different from humans. And 80 years ago or more, Alan Turing postulated a machine that would be impossible to distinguish from a human if you conversed with it. Might have seemed far off at the time. Today, the technology has come far enough that we actually have people, including some of our panelists, working on the problem of how can we tell the difference between the output of machine and the output of humans? And so, at least in certain discrete realms like text chat, we've probably realized some of that wild idea that Turing had. Today, we're going to talk about the relationship between humans and machines. We're going to talk about the limitations that machines still have, what makes them different from us, and whether we should want them to become more like us or not. I'm going to start by we have quite a few people on the panel, so I'm going to start by having each of our panelists give a 1-minute introduction of yourself. So if you could say your name, your title and department, and then just the briefest elevator pitch of one interesting problem you're working on right now in your work. And we can start, Dr. Feldman.
Yeah, my name is Naomi Feldman. I actually have 2 appointments at Maryland. I'm in the Department of Linguistics, and I'm also in the Institute for Advanced Computer Studies. And I build computational models to try and understand how people use and learn language. And so I'm taking a lot of the AI techniques, but then using them to build models in order to do science. One of the problems that I've been looking at a lot is about speech perception. So we know, for example, that for Japanese listeners, telling the difference between ra and la is harder than it is for English listeners. And so trying to study whether the representations that make that happen, how do people learn those representations? And also then when we're perceiving speech in different environments, how can people be flexible in ways that they want to be flexible, like perceiving speech and noise, and then not be flexible in other ways, like if you learn a second language, you don't forget your first.
Hello, everyone. My name is Kai Qing. I'm an assistant professor from the ECE department. I'm not literally from the CS department, but I have affiliation with the department. And thanks, Tom, for the invitation to have me here to send our greetings from the sister department. So I work on the theoretical foundations of reinforcement learning and decision theory and game theory. Recently, I'm very interested in the scenario where you have multiple decision makers. They are strategic and they interact with each other, and what kind of emerging behavior will appear. And especially recently, I'm very interested in this case where we can use these large language models to make decisions. And if you have multiple large language models interact with each other, what kind of interesting behavior would appear? So that's a very recent thing I'm being pretty much interested in.
Hi, I'm Ferran Huang. I'm an assistant professor here at Computer Science. I also have a joint appointment at UMX. So I work on trustworthy issues in machine learning. Specifically, I care about trustworthy issues when things change. For example, in the world that you live in, you might observe something now, but later on it might have changed. For example, in finance, in robotics, and in all these high stakes tasks, including healthcare and autonomous driving. So I care a lot about ethics as well. So one of the things that I work on are to understand how AIs can be made more ethical, especially when they're making very crucial decisions. How can we make sure that AI are in service of people rather than, bringing more bias into the society. So one of the things that I've been working on very lately are to understand how to align large language models with human value and social value. In addition to that, I also care about other issues that are brought by these blooming of large language model, including copyright issues or detectability of fake news. Share a similar interest with Kai-Ching. I also care a lot about reinforcement learning, and specifically, I care about how we can make sure reinforcement learning is more efficient, so it's more sustainable. So one of the things I do is build foundation models for robotics. Thanks.
Hi, everyone. My name is Sohail Faizi. I'm an associate professor in the computer science department here at UMD. And broadly speaking, we work on understanding different reliability issues of AI models, ranging from robustness, interpretability, detectability, so on and so forth. Thank you.
Hi, I'm David Jacobs. I'm a professor of computer science at Maryland and also in UMEX. And for the last little more than a year, I've been on leave working at Meta. And so one of the things that I've been thinking a lot about lately is how to represent video and how to understand video. And there's a lot of interesting questions there. One that's particularly relevant right now is trying to connect video understanding to large language models. So can we figure out how to represent the content of video in a way that's comprehensible to a language model and allows the model to understand and describe what's going on in the video? And there's some interesting work on doing this with images, but and there's some work on video as well, but it's still a very poorly understood area. And so I think there's a lot of interesting questions there.
Hey, I'm Tom Goldstein. I'm a professor here in the computer science department, and I'm broadly interested in safety and security for generative AI systems, both language-based and image-based. And one of the things I worked on recently is how to build effective systems for detecting the outputs of language models and diffusion models. So how do you tell the difference between a generative model created thing and something that is created by a human?
It's a very timely question that several of you are working on. I have a story coming out in a day or two about the rise of voice fakes and generative AI being used to mimic the voices of real people. And one of the places where that happened recently was in the elections in Slovakia. Actually, one of the parties used generative AI to fake the voices of members of another party and make it seem like they had said something that they didn't actually say. So obviously an important problem. How do we tell when it's an AI speaking instead of a human? And then we were going to have Dr. Georges Ray, who's in the Department of Philosophy. He was unfortunately sick today and wasn't able to make it, but he sent a few thoughts that I think Tom will work in maybe at an appropriate moment in the conversation. There's one unadvertised panelist that I wanted to bring in just for this question. So just for fun, I asked ChatGPT to also describe in 1 minute an interesting problem that it's working on. And this is, for those who care, this is the free version of ChatGPT, and this is one shot. So I just asked it once, and here's what it said. ChatGPT says, "I don't actively work on problems, but I can certainly describe an interesting problem that researchers in the field of artificial intelligence are exploring. One fascinating challenge is achieving common sense reasoning. Common sense reasoning involves equipping AI systems with the ability to understand and reason about everyday knowledge that humans take for granted. This includes understanding concepts like physics, social norms, cause and effect relationships, and contextual understanding. The problem lies in the vast and nuanced nature of common sense knowledge. Humans effortlessly navigate this realm, but it's a complex task for machines. Researchers are working on creating AI systems that can understand and apply common sense knowledge in various domains, enabling them to make more informed and contextually appropriate decisions." All right, how do you all think that ChatGPT did there? Do you agree, disagree? Anybody want to weigh in?
I think it did pretty well. I think that's a big question that a lot of people are interested in. I think some of the more vision-focused panelists might have some.
So even without common sense itself, ChatGPT was able to give a pretty plausible answer to that question. Let's talk about some of the ways, so I think that's a demonstration of a way in which one of today's AI models convincingly mimics a human or can sound similar to a human. What are some of the key differences in how a model like ChatGPT operates versus how the human brain operates? What are some of the, are there important fundamental differences that still distinguish our ability to respond to a question like that from theirs? And anybody can jump in.
I'll take this. As someone who builds models of humans, one of the things that really jumps out just when you first look at these models is how much data they're trained on. I mean, these models have to learn on the whole internet. They have to learn on essentially, lifetimes and lifetimes worth of data. And humans are really efficient in how they use data. They're really efficient both in learning. So kids learn their language with a lot less data than GPT does. And GPT still doesn't agree with kids about, what word goes in a sentence or, still doesn't perceive speech in the same way that a 1-year-old does. Also the same thing comes out in terms of flexibility and ability to adapt to new situations. So, human listeners are great at adapting to a new listening situation or a new accent that they've never experienced before. But what ChatGPT does or other, large speech models is it will just take all of these data and memorize them. As long as it's memorized the right thing, it can do pretty well. But I think there are just huge differences in how humans use data efficiently versus how machines just need more and more and more data in order to be able to memorize all the different things it might need to do.
Go ahead, David. Or do you want to go, Fro?
Sure. One of the things that I think how we train large language models is that all of the things that we are using to train a large language model, although we claim that it's everything on the internet, I do believe that there is a vast majority of things that is unwritten. So common sense, right? There are a lot of times that, there's something that we all agree on is a common sense, but it's never written anywhere. And it's really hard for these large language models to pick them up just from the data that is out there in the, on the internet. Actually, there was a joke about there is 95% that is actually unwritten. And what is written seems to be vast, is still only 5%. It's like the black matter. So I think that basically made large language models not really, able to do not very good at interpersonal skills, and they're not able to, do simple things such as common sense reasoning. They hallucinate, and researchers are working very hard to solve these problems.
So if ChatGPT had to read the room and know when was the right moment for it to interject its comments, that might be one of the things that it struggles with. David?
Yeah, so I think it's clear that large language models and AI don't have the kind of deep understanding of the world that humans do. But I think the really interesting thing that we've learned from large language models is how much of intelligent behavior does not require a deep understanding of the world, and how many problems you can solve with a lot of data and a very shallow understanding of the world. And I think that, unfortunately, one of the lessons here is that, maybe large language models can't be that creative, but most people aren't that creative either. And most of what we do is actually done by rote. And it's not as big, it doesn't require as much to replace a lot of human intelligent behavior as one might have thought.
Yeah, it's a little discouraging when you put it that way. Tom?
Yeah, I guess I would just add a comment that I think GPT-4 is actually, it does a surprisingly large number of what we might consider common sense tasks surprisingly well, maybe not with human accuracy, but surprisingly well. I don't think the fact that it's not a fundamental reason why machines can't solve common sense reasoning. It's just a matter of feeding the data into them that they need to learn those things. But what I wanted to comment on was language models in particular, they have this very particular way of generating text where they generate it one word at a time. And the way a language model works, you basically boot the model up and you have it generate one word, and then you shut the model down and you wipe its memory, and it has no idea what has happened in the past. And you boot it up again and you give it all the words that have been written, and you say, what's the next word in the sentence? And it looks at the sentence and it thinks about it and it tries to figure out the next word. and then you shut it down and you wipe its memory, and it starts all over again with the next word, right? So mechanistically, this is just really different than the way that humans behave. So Georges Ray, the panelist who wasn't able to be here today, I was really disappointed he's not able to be here too, because he has a lot to say about the cognitive differences between machines and humans. But he's very focused on the fact that the Turing test, which is one a common framework that we think of for using to evaluate machine learning systems, the Turing test is what he would call a behaviorist assessment. You're only looking at the behaviors of the model, but you're neglecting all of the mechanistic things that happen under the hood and the way that the behaviors are actually different. So when I think of when I want to create a sentence, like I'm going to go to the store, I think of what I'm going to say and then I assemble the words to say that thing, right? But that's really fundamentally different. I think there's going to be a disagreement with me than what machines seem to do, in that the machine doesn't necessarily know what any of those words are going to be until it's the moment that it's going to predict them. Yeah.
So you want to jump in?
Yeah, if I can just respond to that. Actually, the word prediction is one of the places where we actually see a lot of parallels between humans and machines. So machines don't predict the same word that the human would, but we have a ton of evidence that when people are processing language, when they're listening to someone speak, they're constantly predicting what's going to come up next. And so we see that both in terms of how long it takes them to read the next word. If it's a surprising word, it'll take them longer to read. We see that in terms of brain signals that we can measure with EEG machines. So just measuring electrical signals from the scalp, we see that those signals are sensitive to how surprising the next word is. And so I actually think that predicting the next word, you picked the one thing that actually we have a lot of evidence for in humans.
Yeah, go ahead, Sahil.
I slightly disagree with Tom. I think there may be some fundamental issues that current models and architectures have that prevent them to, for instance, have common sense, contextual understanding, emotional intelligence, so on and so forth. So the current models that we have, they're amazing correlation extractors. So they look at the data, they try to get some statistical patterns from the data, and that is how they, generate their output, either if they're predictive or they're generative. So the main question, and in fact, I don't know the answer, otherwise, I would have been probably a billionaire, that if basically we can extend the current architectures to overcome this barrier, this fundamental barrier to integrate some other high-level understanding of, basically the context in terms of reasoning, in terms of, ethics, in terms of emotional intelligence, so on and so forth. Personally, I don't believe with the current, scaling of the data or model parameters, we are going to reach to that level. But that doesn't mean that AI won't be useful. We may not reach to AGI, but still will have a pretty useful AI model.
So I guess I kind of agree with Sohail and kind of explain what's going on with the first panelist mentioned, like why there is a huge sample efficiency gap between training the large language models and how we as human learning things. I think the fundamental reason I believe is the way we represent knowledge is different. So like the next word prediction, I still, as to me, I feel like maybe subconsciously I'm doing that, but I'm not sure if that's the way I represent knowledge and how I generate my natural language. So I believe there should be some fundamentally different architecture that we should be able to explore that is very different from the next word prediction and the transformer structure people are using nowadays. And talking about the title of this panel, so I want to mention there's one very interesting thing I've learned recently. It's called the Moravec paradox. I don't know how many of you have heard about that. So I think people are saying that in contrast to the very traditional assumption where they believe reasoning is a very hard task, but in contrast it's not. So reasoning is actually relatively easy. In fact, the capability of perception and mobility, like a 2-year-old child can do, is much harder. It's a much harder skill to acquire. So I think that may be something we are fundamentally different from the robots or the artificial intelligent agents. And one explanation for that is like people have spent like thousands of years to acquire this kind of very basic skills. But other like seemingly more challenging tasks like playing chess or like solving mathematics, they are relatively new actually. So that's one of the explanations, which I'm not sure if that's the most correct explanation, but I just feel like there is a fundamental difference, and that may be especially in the cases where we have this embodied intelligence, where you are developing intelligent agents with mobility and perception capabilities. Those are the challenging directions we should be developing a little bit more.
Yeah, one of the first big achievements in AI, as I understand it, was back in the 1950s. People were able to develop computer programs that could do logical proofs, sometimes better than humans. And at the time, I read that there were people who thought, well, wow, computers that are smarter than humans must be just around the corner. And of course, we've gone through cycles of thinking that that's the case, and then thinking that that's very much not the case over the years. And now we're in one of the cycles where a lot of people are thinking, well, maybe we're just around the corner from machines finally being as smart as humans. One of the areas in which today's large language models fall short is in ground truth. We know that they will often say things, these chatbots, these language models, they will say things that sound quite plausible in response to a question, but they're not always true. Sometimes they'll flat out make things up. If any of you, this is an academic audience, so if any of you have tried to ask ChatGPT for citations or papers, there's, you might have noticed that it'll just come up with plausible sounding but completely fake papers. One of the funny things that I talked to a researcher who calls these hallucitations, and one of the funny ones is if you ask it to cite a paper on macroeconomics, it will give the author's first name as the most common first name among highly published macro authors. And then the last name will be the most common last name, but they won't match up to any real person. So that's one shortcoming of that sort of predict the next token approach to learning. Is this kind of problem solvable with the architectures we have today? Can we, should we expect that, maybe GPT-5 or 6 or, it will solve the misinformation problem, or will it require something fundamentally different in the way these systems are built?
My opinion on this one is that I think that we can solve the hallucination problem, just so right now I think there's two barriers. One is we have to do the engineering, and some of the systems we have right now are I think maybe under-engineered and not ready for deployment. Like Bard is an example of this. There's actually a fact-checking feature in Bard, but it's pretty inconsistent. I think it's just a matter of how much they need to refine the system. But also I think there's a big economic barrier that is a problem. It just takes a lot. There are systems that have been proposed that can do pretty accurate fact-checking. They can find all of the facts inside of an article. They can look for references on the internet. They can rank those references by reliability scores. Then they can check whether the output of a language model is consistent with those references. But that's all really, really expensive. And if you're trying to build a free search engine, you're running, doing 10 to 100 times as much text processing to produce an output as you need to do if you just ask the language model and do one single generation. It's, I think right now, the cost just means that those kind of methods are off the table. And so I think one of the reasons we see that weakness, that weakness seems so present in the internet tools that we have today, is just because of the cost.
I partially agree with Tom. So I think we will solve the citation problem, but I think that, the general hallucination problem is going to be much more difficult. And the reason is that, as I mentioned, these models are amazing correlation extractors. So they're as good as their data. And even though we are scaling up the number of samples for training these models, there are some weird, uncommon contexts that we will never be able to have them in the training of these models. For example, if humans, we see like an animal in a garden, okay, it is basically a common context. But if we see a horse in our bedroom, right, so we still think it is a horse, but we will be very surprised. right? So it will be very unlikely to have such an example in the training of the model. So I think that the issue again is that we will have some uncommon context that these models will, be very likely to fail on those situations because those smaller subpopulations, they have not been represented well enough in the training set of those models.
I'm also very interested in this problem. In my opinion, I think there are techniques that are trying to solve this problem. For example, chain of thought. For example, causal reasoning, extracting causal relationships rather than just statistical correlations.
When you say chain of thought, that's like when you
thought
ask the model to lay out its step-by-step reasoning, is that right?
Yeah, okay, yeah, good. For example, we have a recent work on trying to understand whether you can use the pre-trained vision language model to do zero-shot classification, meaning like, don't change the model, just to use it directly on something that is in the wild. Right, so actually one thing we found is that chain of thought would help the model in terms of figuring out what is the sparse correlation. For example, if you've seen a water bird that is always, come with the water, then probably the model will always predict as water bird, even though it is not necessarily, right? So, in those kind of things that if you kind of prompt model to think twice and kind of, look at your background, look at all these other things, then it's possible that these models would actually correct themselves. But that being said, I don't think that's the ultimate solution here for solving hallucination. I think that you probably wanted to use some source of knowledge that is outside of how these models are built. For example, knowledge graph. I don't know whether knowledge graph will solve it, but assuming that you have a knowledge graph that is incorporating all the common sense, maybe that is not possible, but if it is possible, I think you would want to combine your models with this knowledge graph to do a fact check and these kind of things, and probably hook your model with internet to do a fact check.
So I think one of the key reasons right now these large language models have this hallucination problem is because mainly because that they are using something called reinforcement learning with human feedback. So you want to align their value with, or align the way they output things as if a human is outputting something. So this is, I would say this probably is one of the common issues in many cases of training machine learning models is that we have a fixed objective to optimize. So that's not exactly the same as how human human intelligence are making decisions. And that's probably, at least from my understanding, that's one of the barriers we need to conquer, we need to address. And the key reason they are having this hallucination problem is that these models, they do not know, they don't know. So that's the key reason. So you give them an objective to predict the next word, and then they will just output whatever they think with the highest probability. But the reason why they output something like that is because they don't know how to say that I don't know the answer to this question. So if we, at least for this specific question, if we teach them how to do that, that's part of the solution to this problem. But in general, I would say, in all this training, if you're only optimizing a specific objective, even in reinforcement learning, if you're optimizing a specific reward function, but these objectives are not carefully chosen, then probably you'll have similar issues. So we need to kind of address these kind of problems.
Yeah, I'm going to come down very hard on this one and say I don't think that this architecture can do it ever at all. So the reason is I think it's just so closely connected to the amount of data problem. These models need to memorize everything. It's very closely related to what Sohail was saying, that if they need to memorize everything, then they need to have seen everything in order to not hallucinate things in new situations, because they're always going to encounter a new situation. And I guess we still don't know whether we can solve the amount of data needed to learn problem in these architectures, but I have to say I'm a little bit skeptical about that. I'm skeptical about that in English, and I'm even more skeptical about that in most of the languages of the world.
All right. So one of the approaches that I've heard about being used lately to try to make machines smarter in some of these ways is having the machines interact with each other. OpenAI, a few weeks ago, Tom pointed out to me, bought this startup that makes a sort of open source version of the Minecraft game. And he was speculating that maybe one of the reasons is so that it can have virtual agents interact with each other in this space and learn that way. It struck me that if I've got this correct, and somebody correct me if I'm wrong, remember I'm the least knowledgeable here, but as I understand it, when DeepMind taught its machine to beat the game Go, it came up with AlphaGo. It beat the world's greatest Go player, but then it came up with, what was it, AlphaZero, where it had, instead of AlphaGo had just studied all the human Go games of the past and learned from that. AlphaZero actually had AIs play each other an almost infinite number of times and learned from that and ended up crushing AlphaGo. So I wonder, Kai-Ching, maybe that's something you could speak to, is this approach.
Yeah, thank you for calling me. Actually, along that line, recently DeepMind had an even more recent version of that. I think it's called diverse Go or something like that. So basically, literally, it's like we have seen that cases a lot at least in playing Chinese chess, where like two players are playing against each other, but there are a bunch of audience. They are looking at the board and they are making suggestions or making advice. Although that's not allowed, but some people are just doing that. They just cannot help. And what they are showing here is that because of this multi-agent communication interaction, they can build up a even stronger Go bot, like a Go player. So that's maybe another way to do that. And a recent example of that. And along that line, recently in the large language model world, like a group of people from Stanford, they developed something called generative agents. So literally, they build up a simulator where they simulate not many, just 25 agents, and they interact with each other. And then they are allowed to talk, and they keep simulating this kind of environment. And they observe something very interesting there, in the sense that, for example, one of the agents say, "I'm going to throw a Valentine's Day party," and then people just spread the words. And then they started to invite the partners, or
by people, you mean the other virtual agents,
other
right?
virtual
Yes.
agents, sorry, other virtual agents. And then they started to invite people and started to even date with each other and trying to team up and trying to pair and trying to participate in this kind of party. So there are a lot of very interesting emerging behaviors happening if you allow this agent to interact with each other. And I also go into the question, I believe that's another key difference from the current AI agent development. And that's something we're trying to, I think we should think more along that line. And that's something I've been working on lately. But that's a very good point.
Go ahead, Sohail.
The limiting factor here would be the environment that the agents are, being simulated. Right? So, if the environment is very sophisticated, then agents will know about what is the world model within that environment. That will help because it will basically try to explore different parts of that space. But if environment is, very basic, then the agents won't be good. So I would say that kind of learning will be as good as the level of complexity that the simulation environment is for training those agents.
And language has proven to be, with these large language models, it's proven to be very powerful. And I was talking to David just before about how language has played a big role even in the generative AI that generates images, right, in the world of computer vision. But are there things in computer vision, do we run up against the limits of just using language as a way of understanding the world when you're trying to understand the visual world as a machine?
Yeah, so one of the interesting things that's happened in computer vision is that people have been able to use as training data, not just language, but language that's associated with images like captions. And by training systems with captioned images, they learn to understand images in a way that captures some of the semantics, some of the things that people might say about those images. But one of the big bottlenecks is that we don't have that same level. So we have billions of images like that, but we don't have the same level of description for video. And so we haven't been able to learn about video in the same way that we've been able to learn about images. And I think this relates also to something that people were talking about earlier about the lack of common sense understanding of the world, because there's so much knowledge of the world that's not written down. But a lot of that knowledge of the world is probably captured in video. So if you want to know, like, how do I pick up a laptop, the fact that, I have to put my hand under it and on top of it and grip it is something that you might never see written down because it's just so obvious. You're writing a novel, you just say they picked up the laptop. You don't explain how they did it. But that knowledge, a lot of that knowledge is present in video. And I think if we can figure out how to train systems not only with huge amounts of linguistic of text, but also huge amounts of video, there is the potential for even greater advances in how these systems understand the world.
Farhan?
It's a very interesting point. Actually, since I work in robotics a little bit, so there has been work that are trying to use, vast amount of YouTube videos to teach a bot to cook, for example, or to drive, or to do all these kind of interesting things. And we've seen a lot of success there. And of course, we're still not there yet in terms of building a real kind of general AGI version of robotics. But it is a very interesting angle here.
Yeah, I was listening to Jan LeCun talk about the problem of predicting the next frame in a video. I mean, we've got these language models that have become outstanding, although still imperfect, at predicting the next word in a sentence and stitching together, whole paragraphs and responses that way. Predicting what comes next in a video turns out to be a lot more difficult, in part because the number of possibilities for the arrangement of pixels is so vast compared to the number of possible words that could come next in a sentence. So yeah.
I just asked ChatGPT how to pick up a laptop on a table, and gave me 11 steps. Prepare, clear the area, stand in front, use both hands. Apparently, we can pick up a laptop with one hand. Lift carefully, maintain a firm grip, so on and so forth.
I'm glad you brought ChatGPT back in. I was neglecting it as a panelist. So.
So, I mean, you said it's a hard prediction problem, the next frame in a video, because there are so many pixels. How many of you think that when we perceive the next thing that's about to happen, we perceive it in terms of pixels? I mean, I think the problem is these machines just don't have the right representations, and that's also very closely connected to the fact that they need to memorize all the different configurations of pixels in order to learn.
Yeah, so that's a theme that's come up a few times, is that these machines, to the extent we can say they're thinking, they do it probably quite differently than how we do it. One of the things that was interesting about my basic understanding about Turing was that the reason he came up with the part of what's now called the Turing test is because he was really after the question of, can we build a computer that thinks? But the problem was we don't really know what thinking is. That he found it so hard to define what is thinking and how will we know, that he said, let's just forget about that question and look instead at, can we build a machine whose outputs are indistinguishable from those of a human? Now, several of you work on the problem today of distinguishing machine outputs from those of a human. Is that, Tom, is that a problem that you think we'll be able to solve near term when it comes to the outputs of DALL-E or voice generation systems like HeyGen or ChatGPT? Or is that a problem that's gonna continue to haunt people who want to be able to tell when something's been generated by a machine versus a human?
Yeah, I mean, my opinion on this is that we can generally tell. Even today, we have systems that do a pretty good job discerning the difference between human and machine for language models and for images. One of the people oftentimes talk about how accurate these systems are, but if all you care about is, say, the false positive rate, how often do you falsely accuse a human of being a machine? We can get those rates pretty low. That doesn't mean that the systems are faultless. Like Sohail's done a lot of work looking on the adversarial robustness of the system. So maybe you can deliberately manipulate something in a way to bypass a particular detector. And I think that there's always going to be a cat and mouse game playing out in that sense. But at least with the kinds of generative models we have now, they seem to produce things that are sufficiently different from humans that we can reliably detect them. The question is just whether in the future, as systems get better and better, will they become closer and closer emulators of human behavior to the point where we cannot distinguish, or will they remain different? And my personal opinion is, I think that I'm making a prediction here, but looking down the road, the way that we train language models is so different from the way that we train humans. Next word prediction is very different from what humans are trained on. The kinds of data corpuses are trained on are very different from the kind of data that we learn on. I don't see a future where, at least in the near-term future, where machines converge so closely to humans that we can't tell the difference anymore.
All right, so to grossly oversimplify, Tom doesn't think that telling the difference between AI-generated material and human-generated material will be a big problem in the future. Does anybody disagree with that?
I partially disagree. I like Tom's optimism, obviously. So I think this problem is already very difficult for both text and images. It is not just the problem of detection rate. So we recently, posted a paper about detection of AI-generated images. The issue is that not only, let's say, you pick your technology to differentiate AI-generated images with real images. For example, watermarking, where you're injecting and embedding some hidden signals in your image so that later on we can tell the difference. So the issue is that not only we can erase the watermarking signal from these images, that's basically evasion attack, but at the same time, we can do spoofing attack, meaning that if you give me a real image, I can just add a slight noise to it, imperceptible noise, and that image will be flagged as a watermark image, meaning that it is generated by AI. So therefore, if you have an image, you have no idea if it was flagged as a real image, if it was originally watermarked, and vice versa. So the information content that we'll get with those types of detectors is going to be pretty limited in practice. So that's a big concern, in my opinion, especially with the advances that we have in language models, in text-to-image models, spread of misinformation, deep fake. I think this will be a big issue. I wish Tom is correct, but I think we'll have a lot of issues, especially when we get closer to events like election in the US and Congress.
All right, I don't know if there's an organizer out there who can signal. Do we have an extra 15 minutes or so to complete the hour, or do anybody know if we have a hard stop here, or we can take some audience questions? All right, seeing no response, I'm going to assume we can just plow ahead. If anyone in the audience has a question, all right, I saw a hand shoot up already. Let's make sure, having done a few panels in the past, let's make sure that they are actually questions and not statements, and try to keep them brief and concise. All right, I'll bring you the microphone.
Thank you. I have a couple, I'll just name one question. It seems to me that if you're not dealing with something that's factual, to ask ChatGPT or GPT-4 to write a poem or write something like that, I would say it's very difficult to tell the difference between that and a human being, and especially in the time it takes. It will generate something that anybody would take at least an hour to do, and they'll do it in 10 seconds. And I think you have no way of knowing whether that's real or whether a person did it. So I really think these non-factual kinds of generations of AI will be very hard to discern as human or not.
Thank you. Yeah, and of course that also brings up the point that there's a difference between, if you have all the time and resources in the world, can you tell whether something was AI generated or human generated, versus if you're scrolling through your Twitter feed, with your eyes flicking past each post in 1 second, are you going to be able to tell the difference? Does anybody want to address that?
Sure. I don't think this is okay. Yeah, so interestingly, there are, even when you mentioned writing a poem, even when a language model is generating non-factual information, there are certain kinds of word patterns and certain behaviors that language models have that are just a little bit different from humans, right? So what happens is every time you see it, the next word get printed on the screen, you might ask yourself, is that a machine or is that a human? And you can compare that to an existing language model, and you might say, it's a little more likely that that's from a machine than a human, but that only gives me a few % certainty, right? But then you see the next word, and it's also a little bit more likely to come from a machine than a human. And the next word, and the next word, and the next word. Once you get about 200 to 300 tokens, there are algorithmic systems that can tell the difference between human and machine text with a false positive rate of about 1 in 10,000. So pretty accurate, not perfect, but pretty accurate. What's interesting here is just that the algorithms are so much better than people, right? I'll look at text and I'll have no idea whether it's machine or human generated, but there are algorithmic approaches that are quite good at that, making these very subtle determinations. And the more text you have, the more information there is, and the more accurate your determinations can be. So these systems aren't perfect, but the state of the art very recently has gotten much better than you might expect. It's gotten much better than I would have expected even 3 or 4 months ago.
True.
So I have a love for statistics. So I wanted to say something that is related to statistics of detection. So when people think about, impossibility of detection, oftentimes we're looking at a specific instance. We're saying that, hey, this is really hard to distinguish whether this is coming from human or machine. But from a statistical perspective, first, when you talk about detection, is oftentimes in statistics. So, if you've generated 1,000 different things from the machine, then what is the percentage of them that you were able to distinguish from human-generated things? So that's one thing that I think the general public oftentimes, use a specific instance to claim impossibility. So the other thing, since I'm trained in statistics, our group has been working on something that is theoretically showing that if you have more samples, and you don't actually need to, have many samples. If you have a text that is long enough, even if it is not independent samples or anything, a long text, then the confidence that you're able to detect it from whether it's coming from machine or human is actually 1. So it's very surprising, as long as you have not enough text, then you should be able to do such detection. But that being said, I think we fundamentally lack a technique that actually considers multiple samples in the detection process. All the detectors are actually assuming just, one instance, let's do the detection, but we don't have that detectors yet, but theoretically it's possible.
All right, I know that coming up next is the Hall of Fame ceremony. With apologies to the Hall of Famers, we're just going to take maybe one more question and then we'll wrap because we got started late here. I think there was a question over here.
This one is a very simple question. How many of you have seen the documentary, The Coded Bias? So the question is, how do we go from here as far as bias and ethics from an artificial intelligence perspective? Because I do know that, I think artificial intelligence systems doesn't have much of an emotional intelligence quotient, EQ. Thank you.
Yeah, good question. We talked at the beginning about the vast quantities of online data that language models have been trained on, but that's still not everything. And in fact, it oversamples a lot on. We know that some of the big data sets oversample on sites like Reddit, where you're getting, maybe not the most unbiased information sources, and maybe learning some bad habits from some of the uglier sites on the internet. Does anyone want to address the question?
Maybe I'll comment on that. I think it's a very important problem. It's a fundamental problem, and the root cause is that the models, they basically extract correlations from the data, right? So for some obvious subpopulations, right, based on gender, race, other, control subpopulations, maybe we can evaluate the bias and we can try to mitigate the bias of these models. But the issue is that there may be hidden factors that model is using and we have no idea about them. So we recently studied some vision models, and we, for instance, like, detecting, races and, other, outputs. And we noticed the model is biased for predicting Indians when they wear glasses on, compared to the ones without glasses. So this wouldn't, be something that you can write down and try to evaluate the model performance on, Indian samples with or without glasses, right? So, that's the difficulty of the problem, because there are many, many hidden factors that model may be using and we have no idea about, and therefore model is going to be biased against them.
Yeah, one other thing I'd say is that this is a technical problem, but it's also a social problem, in that technology companies are incredibly competitive and under a lot of pressure to make money. And it's difficult to invest a lot of resources in something that doesn't directly produce income. And if we really feel this is an important problem as a society, I think we have to start regulating things. And we have to create a system, a social system, in which these issues have to be addressed. We can't just rely. I mean, companies don't want biased systems. They would much rather have unbiased systems. But there's 100 things that they're trying to do, and that's only one of them.
I'll just point out that I think we're talking about biases in English-speaking ChatGPT and English-speaking technology, and we're sort of ignoring the fact that English has all of these systems and a lot of languages don't. And so I think there are huge ramifications of sort of developing these systems on things that we have said and not things that people who speak other languages and in other cultures have said.
So maybe the last part I want to quickly add is, like, right now this issue is very important, especially in the case where you have human in the loop. So in the language model training, I mentioned you use reinforced learning with human demonstrations. And the humans are, by nature, when they generate those data, they are very biased. But what I know so far is that in OpenAI, they didn't deal with this issue yet. So they try to use scaling. They try to make use of more data to address this issue. But I believe there should be more advanced approaches trying to address this bias issue, especially if you have human in the data collection process.
Yeah, I just wanted to add one thing that I think as a society, we tend to focus on what sometimes are called the representational harms of generative AI. So for example, generative AI might assume that someone is, say, male because they're a doctor, right? That's an example of a representational harm. And it's not that those representational harms aren't harms, it's just that we tend to focus on them because they involve representations that we can see. I think that the most socially impactful manifestations of bias are in the invisible AI systems. For example, if you submit a resume for a job search, there are a lot of systems now that do all the resume matching and sorting using some sort of AI system. And the biases in that are going to have strong economic impacts on the people that are applying to those jobs. Another example would be in credit lending. Machine learning models are very actively used in credit lending and credit forecasting right now. And so the output of a model might determine whether or not someone is able to get a loan, right? But these kinds of biases are a little bit more invisible to us because they're not representational biases. And I think that as a society, we are more inclined to overlook them despite their tremendous impacts because they're non-representational.
All right. Is this on? So we're gonna bring it to a close. We've talked a lot about the ways in which machines seem to be approaching human intelligence in certain realms, about the ways in which they're still different, and the ways in which they still aren't approaching human intelligence. And I just wanted to add one of the things that has been hammered into me again and again in my reporting on the implementation of AI in the real world is that AI is being used to replace human work, not because, in many cases, not because it's better, or not even because it's as good, but because it's much cheaper, much faster, and the people implementing it hope that they can get away with it being worse, that it's just good enough. So and the biases that are encoded in AI are one of the problems that we're going to probably continue dealing with as as that happens. Thanks so much to all the panelists, and thanks to everybody in the audience for listening.